Hello there and welcome to Forces 2, Part 1. This is going to be on Lesson 7, which is on Newton's third law and inertia. So there is some higher tier content in this booklet, in this lesson. So just make sure that you're watching the correct portion. Although for this booklet, I know that the higher tier starts at the beginning. However, I'm going to keep that towards the end because I think it's more beneficial if I explain Newton's third law first and then kind of bunch all the higher tier stuff together. Okay, so if you everyone should be watching this video from the beginning, and then once you get to the higher tier stuff, if you're a foundation tier student, then you can just skip on to the checkpoint questions. If not, then you can just watch the whole video. Alright, so we're going to start off with the do now. 8 questions, quite simple. These have a lot of formulas that you need to know, so go ahead and pause the video and do that, please. Okay, so here are your answers. Like I said, these are all formulas that you need to be familiar with. And with physics, I know it's difficult because you do have to memorize quite a lot of equations. So just make sure that you are giving yourself the time to memorize these formulas as well as learn how to rearrange them and also how to use them and what units they're in. Okay, so lots of important stuff to do with equations and things like that. Alright, so for this lesson we're going to be looking at inertial mass for higher tier, but for all students we're really going to be focusing on Newton's third law. So this is Newton's final law of motion. We've gone through the first and second law in the previous lesson, so just make sure that you are familiar with those before we move on. Okay, so let's start off with Newton's third law. Newton's third law states that whenever two objects interact, the forces they exert on each other are equal and opposite. So this one I've actually mentioned maybe once or twice in previous lessons, but this is more commonly known as action-reaction, okay? And the longer way to say that is basically for every action there is an equal and opposite reaction. Okay, so the picture that's on your booklet right now that has the tire on it, so there are contact forces, which means that they're touching each other between the tire and the road. So when the tire is exerting a force backwards, okay, so the force from the car on the road is going backwards, it's going to actually push the car forward because the road is exerting another force, which is opposite and equal to that force going backwards from the car. And that's actually what propels the car forward. Okay, so the tire pushes the road backwards and the road pushes the tire forward. So opposite and equal actions there. Okay, some other examples are two people on skateboards, and when they push off of each other, they're going to exert an equal and opposite force off of each other. Okay, so A and B, they're going to go in opposite directions, probably towards their back. Right. And then another example would be a swimmer who is pushing off the wall to go forward. All right. The important thing to notice here is that you're always looking at a system of interest. Okay. So in the case of the skateboard, you really want to be focusing on one person, right? So if we're focusing on person A might exert a force on person B, but it's going to be person A action that creates a reaction. And same for B, right? It all depends on what you're looking at. So in terms of the swimmer, we're looking at just the swimmer, right? We're not looking at anything else. We're not looking at the water. We're just looking at how much force is the swimmer exerting on the wall, and also how much is the force exerting back, how much force is the wall exerting back on the swimmer. All right, and because of that, you have a direction of acceleration that is forwards for the swimmer here. Okay, now a common misconception that most students will have is that forces cause motion. Right? So if I have a force going in a simple direction, then that means that it's causing motion. This is true and it's not true at the same time because we want to make sure that we define motion very specifically. When you have a resultant force. So remember how in the previous lessons, if you have two forces that are going opposite directions but they're unequal, then you're going to get a resultant force, right? Now that resultant force, although it does create, it does cause something to move in a direction, but we want to be as specific as possible. So we want to say that if there's a resultant force, there is an acceleration towards that direction. So let's just say that I had a resultant force going forwards. That means that I am accelerating forwards, right? Yes, it does mean that I am moving forwards, but again, we want to be very specific. So instead of moving, we want to say accelerating. And that way we know that the forces are unbalanced there. Because if it was just motion, then you can actually describe it, or you can interpret as there is no resultant force, but the object is moving in constant velocity, right? So just because there's a resultant force does not mean that it's just moving. It actually means that that object is accelerating. So make sure that you are specific, because for Newton's third law, we do have to actually get into specifics in terms of, well, how do we differentiate Newton's third law from something that's in at rest, right? Because all of these, right, they all have a resultant force of 0, right? If it's equal and opposite, that means the resultant force is 0. So I'm going to explain a little bit more about what this means as we go on. All right, so another example, you have a spacecraft that is orbiting the Earth. So you have a spacecraft very, very far away from Earth. And for this one, we're actually talking about non-contact forces. So remember that non-contact means that they are not touching. So there are non-contact gravitational forces between the Earth and the spacecraft, and this is something that you probably may not have known before, but the Earth pulls on the satellite and the satellite pulls on the Earth. So this actually still refers to Newton's third law, right? For every action, there is a reaction. And for this, you have to maybe understand a little bit more. But I'm just going to really quickly gloss over this, okay? So every object actually has a gravitational pull. And the law is, or the rule is, that the bigger the object, the bigger the pull. And so, again, we have to look at our system of interest, right? If we're looking at just the Earth, right? The Earth pulls on everything on Earth, but at the same time, we actually pull on the Earth as well. But when we're talking about Newton's third law, we only have to look at one object. So if we're looking at just the Earth, then when the Earth is exerting a force on us, there's an equal and opposite reaction, right? We exert a force back on the Earth. The only reason why the Earth isn't pulled towards us is because the Earth is gigantic, right? So the Earth actually has a much, much stronger pull that kind of negates or cancels out whatever force that we're exerting on it. Okay? So that's kind of how gravitational forces work. And if you go into higher level of physics, you actually learn something about this. You don't need to copy this part down, but basically, if you have two objects, they will both exert a force on each other, depending on how big both of those objects are and how far away they are as well. All right. So you'll learn about that formula once you get into either A level or university physics, but this is actually quite interesting, and it lays it out quite simple that the things that determine how strong a force is how heavy something is, or sorry, how much mass there is, and how close you are to it. Okay? All right, third example is a space rocket. So the force excreted by the exhaust gases on the rocket moves the rocket upwards, and the force excreted by the rocket on the gases push the gases downwards. So the two action and reaction forces here is the force on the rocket, right, and the force on the gases. So there you are labeled with your action and your reaction. So when the force coming out from the rocket is pushing on the gases actually will push back on the rocket, all right? And for a space rocket like this, in order to overcome the pull of gravity, the rocket must exert a force downwards that is greater than the pull of gravity. Now, generally, this will be done in a way that the space rocket can actually push off of something, which is why generally you don't really see space rockets being launched mid-air, right? They're always starting from the ground, and so they'll actually push off the ground, right? So the forces that are coming out from the rocket are pushing on the ground, and the rocket is going upwards. And since there's nothing really stopping the rocket from going up, that's the only direction that it can go, right? And so that's how generally Newton's third law will work in this instance, right? So your action is your force on the gases, and your reaction will be the force on the rocket itself. Now, if I actually gave you an example of how to, explain this, let's just add some numbers here, okay? So let's say, for example, I'm trying to determine, well, how much force does this rocket have to overcome in order to actually go up, right? And the formula that we want to use is weight equals mass times gravity. And so if I gave you, an example at the space rocket weighs 100,000 kilograms, then this rocket weighs a total of 98,000 newtons. That force, that 98,000 newtons, has to be the minimum force that this rocket has to overcome in order to escape the pull of gravity, or overcome it, basically. Okay? And so the downward force, right, pushing downwards has to be greater than 98,000 newtons, which means that the upwards force will also be greater than 98,000 newtons because they're both going to be equal and opposite. All right. I know this sounds a little bit tricky right now, but by the end of the lesson, if you still don't understand it, there are some excellent links that you can use and some videos that you can watch in order to further understand Newton's third law, because the easiest way to understand this is by examples. All right. Okay, so now we want to look at something called equilibrium. And you may have heard this term before, and if you have, that's great. If you haven't, let's look it up. So if the size and direction of the forces acting on an object are exactly balanced, then there is no resultant force acting on the object, and the object is said to be in equilibrium, right? So there's that word there, equilibrium. And if you haven't heard this before, you might see another word in there that says equal, right? So that actually has a lot to do with the word. Equilibrium is a state of rest or balance due to the equal action of opposing forces. So that just means that every force that is acting on a certain object, every force is equal and opposite. And so what happens is they actually all cancel out, okay? And that's what it means to be at equilibrium. And every example that we've looked at so far has had a resultant force of 0, right? And yet, we know that things will move. And so that's why you have to look at certain systems of interest or at certain specific times, right? And this is what really confuses lots of physics students, is because in their minds, you know that that space rocket is going to move. You know that the spacecraft is going to be orbiting the Earth. You know that if two people pushed off on skateboards, you know that they're going to move. But you have to disregard all that and specifically look at certain points in time. Okay? Let's just finish off this paragraph here because it's actually quite important. Newton's third law can be applied to equilibrium situations when, so this is actually a very specific time, when both forces are the same type of force. Okay, so for instance, if I was looking at this diagram here, or this picture of this person pushing on this big rock, right, then this person is exerting a force onto the rock. And by Newton's third law, we know that the rock is exerting the exact same force back onto this person, right? What I cannot do, right, because if I'm looking at the rock, I know it's not moving. So if I were to draw a diagram of the rock, I can't really look at the gravitational forces because, first of all, they're in different directions, right? The force that this person is exerting is on the horizontal axis, which means it's going left and right, whereas gravitational forces are going up and down. So because they're in different directions, I can't really apply that for the first thing. The second thing is the woman is not exerting a significant gravitational force on the rock, right? So they have to be the same type of force, which means that no matter how you look at this, right, this woman is exerting a kinetic type of force to it, right, a pushing force, but the rock is exerting the same type of pushing force back towards this person, okay? And that way I don't really need to look at the gravitational forces of both of these objects, right? So that's what it means by you can apply Newton's third law to equilibrium when both forces are the same type. So the next example is going to show that. So the example that we have here is you have a person pushing against a wall. I'm just going to read this out here. The action force is a person pushing the wall, and the reaction force is the wall pushing the person, right? So action and reaction. For every action, there's an equal and opposite reaction. So you see those two forces there. The forces are the same type, and they are acting on different objects, right? So you have the reaction forces, and then your two objects are going to be the person and the wall. there are other forces acting on the objects. For example, the person pushing on the floor and the floor pushing on the person. So these are actually different systems of interest, right? Because we're not looking at just the reaction forces. Now we're looking at a reaction force in a different situation. So if all the forces on the object, if all the forces on the object are balanced, then the object will remain stationary. Okay? Now, we want to make sure that we are looking at the right system. And in this case, we only want to look at the person pushing on the wall. We don't want to think about the person pushing on the ground because, yes, like I said, we do know that. We do know that the person exerts a force on the ground to push this wall. But when you bring in different systems, then you can't really apply Newton's third law anymore. Okay, so your reaction forces are going to be these two right here. Okay, I've just kind of made them a lot bigger. I know the arrows on top there, but I want to make sure that you guys understand where these forces are coming from. So the force towards the right is the force exerted by the person, and that's where you want to start. And then the wall will exert a reaction force backwards, so in the opposite direction, but it is also of equal force. All right. So if we wanted to make sure that this person moved, right, or make sure that this wall moved, then we want to make sure that the wall will accelerate towards the right. Okay, and really that's the only way that it can go, because we know that the wall won't exert a force towards the person that's bigger, right? Because that would mean that the wall has consciousness and is able to push back on the person even greater. Okay, and this is where people will be like, well, if both of these forces are always going to be equal, how is it going to move? At what point does the wall give in and the person is able to actually push this wall? Because what I'm telling you right now is no matter how much force this person exerts on the wall, it will always be equal. So the resultant force will always be zero. So how am I going to move this wall? And I'm going to explain that really quickly. So the wall can only exert a certain amount of force back, right? Because the wall can only exert as much force as the person gives it. Now, a wall has certain limits in that a wall can only take so much force. And so the wall can only exert back a certain amount of force until it is overcome by the force exerted by the person. So let's just say that if a wall can only withstand a force of 500 newtons, then the person will start exerting a force, and it might steadily go up and up and up from 0 to 100 to 200 to 300 to 400, and all the way up to 500. So if they're at 499 newtons, then the wall will still exert back 499 newtons. But as soon as you cross that threshold of 500 newtons, which is the limit of that wall, then the wall can't exert back 500 newtons. Okay? And so what happens is, let's say the person came in and exerted 600 newtons. Then 500 of those newtons will be exerted back on the person, but 100 of it will be still going towards the right. And that will be your acceleration towards the right. Okay? So again, forces don't cause motion, they cause acceleration. All right? So that is kind of where I'm hoping that most students will kind of recognize, okay, yeah, that makes sense, right? Every physical object has a limit as to how much force they can exert back. Same with the ground, right? Same with if you're standing on top of a box, right? The box can only exert a certain amount of force back upwards as you are pushing it downwards with your weight. But as soon as that box is at the limit of how much it can exert back, then that's when you will accelerate downwards. All right, and that's obviously due to gravity. So again, you're looking at specific systems of interest, and I'm hoping that this explains, well, I know that it's going to move, I know that it's going to fly or whatever, and every system has a limit, or every object has a limit. Okay? So let's clarify some of the stuff that I just said right now, okay? So you have a person sitting on a chair, and it's in equilibrium because it's not moving, right? All the forces are balanced. But this is not an example of Newton's third law. And this is because gravity and normal forces are different types of forces, right? So weight is actually the downwards force caused by gravity, all right? Whereas the normal force, and this is something that you may not have heard before, normal force is another name for the counteractive force of our weight, right? So they are technically different types of forces, because weight, you can't really see weight and normal force as an action and reaction force. They're not reactive forces, okay? Um, and again, they're acting on the same object, right? And so really you want to have two different objects, right? And the same type of forces. This has gone in the opposite direction. Whereas this one has two different types of forces, right? And one object. And so reading along here, because this is where most students will get confused. This is an example of Newton's first law, where an object remains stationary when the resultant force is zero. Okay, so in order to apply Newton's third law, we need to consider the weight and contact forces separately, which means that we have to look at different systems. Due to gravity, the Earth is pulling down on a person, and the person is pulling up on the Earth, right? So there, right, you have two different objects. You have the Earth and the person, two different objects. But you have the same type of force because it's all gravitational force, okay? And then the other one would be contact force of the person on the chair and the reaction force of the chair on the person. So there again, you have two separate objects, the chair and the person, and you have the same type of force, which is the contact force. Okay, so I'm hoping this clears it up a little bit, and it will take some practice trying to figure out identifying different types of forces, okay? But really you want to see, well, what is causing this force? Is it gravity, or is it like some sort of contact force? And so what I try to explain Newton's third law is it's one-dimensional, which means that you start off in one place and see, well, is there anything reacting to that force? And in this case, the weight, right? You know that weight is caused by gravity. So if and you know that gravity is caused by pulling on the person. And if that's the case, right, then what else is pulling on the Earth? And that answer would be yourself, right, the person. So you're only focusing on one force and the reaction to that force. And inevitably, that will include two different objects. Okay, so is it the person and the Earth, or is it a person and the chair? And this is, like I said at the beginning of the lesson, you need to be very specific about what you're looking at. Okay? Again, there's lots of materials that you can use, or lots of resources that you can see that helps explain Newton's third law a little bit more, because this is one of the more confusing ones, and this is where most students will have trouble because they fail to recognize what the two objects are and what the force is. Okay, so if anything, I want you guys to remember, what are the two forces, and what are the two objects, and what is the force that is binding them together? Okay, and always think one-dimensional. Start off with one object, all right, and how is it related to the second object? And if you can't make that correlation, right, or if it doesn't match, then you can't apply Newton's third law. Okay, so at this point, we're going to be going into higher tier. So if you're a foundation tier, you want to skip forward until you get to the exam style questions, and I will see you there. But if you're higher tier, stick around and listen, because we're going to learn about inertia. All right, so inertia, let's define it, is the tendency of objects to continue in their state of rest or uniform motion. And we link this with Newton's third law for various reasons, but really try and keep it as separate as much as possible, because when you start trying to link things together that don't really match, that's when you get a little bit confusing, okay? So from Newton's first law, if an object is at rest, so if it's stationary, it will remain stationary unless a resultant force acts on it, right? So that's Newton's first law. And if an object is moving at constant speed, it will remain moving at constant speed. And this is because every single thing on Earth has something called inertia. All right? And there's actually a formula that we can go with this, but let's just make sure that we understand what inertia is. I'm going to put it in simple terms here. So inertia can be also defined as the resistance of any physical object to any change in its velocity, whether it's 0 or whether it's 5 or 10 or 11 or 100. Okay, so whether the object is at rest and where the velocity is 0, or whether that's moving in constant motion, okay, it's the resistance to that. And so the misconception here is that most students will think of this as momentum, but momentum only pertains to something where it is already moving. Okay, so like for instance, if you are looking at a swing has momentum. Okay, but in order to stop the swing, you have to stop the momentum. The swing itself doesn't really have inertia in that it's not moving at uniform motion because the swing is always constantly changing speeds, and it's not at rest. Okay, so momentum only pertains to things that are constantly moving. So here's the formula for inertia, and we have to look at it as inertial mass. And this is more so, how difficult it is to change the velocity of an object. And as you can tell, the formula looks a little bit familiar because you've had things that have mass and acceleration and force. Okay, and that's because we got it from Newton's second law, F equals ma. And so this should hopefully explain that the heavier an object is, the harder it is to have it accelerate. Okay, so a heavy object is hard to move because it has inertia. Yes, most of you will say a heavy object is hard to move because it's heavy, but that's really a simple way of saying that this object has a lot of inertia. Okay, and so for this formula, obviously I don't really need you to memorize this because you already know the Newton's second law is F equals ma. Right. So really what you need to make the distinction here is that inertial mass and Newton's second law basically have the same concepts in it. And for units, you guys already know force is in newtons, mass is in kilograms, and acceleration is in meters per second squared. So these are all units and symbols that you have used before. So hopefully that you remember most of this, okay? So when we're looking at inertial mass, we have to make sure that we differentiate this, okay? So inertial mass, the ratio of force over acceleration, right? So ratio is just kind of like if you divide something, right? You have something to something. So in this case, we have force over acceleration. So that's our ratio. That's called inertial mass. And inertial mass is a measure of how difficult it is to change the velocity of an object. And please don't confuse this with momentum. Okay, because momentum, like I said before, only pertains to things that are already moving, whereas inertial mass pertains to things that are at rest or things that are moving in constant velocity. Okay, so just make sure that you are aware of the two. This is the last slide on higher tier, and this connects Newton's third law and inertia. So mass is a measure of inertia, which is why I say, heavy objects are really, really hard to move. That's because they have inertia. So a large mass on a person's hand will have large inertia, so they resist a lot of motion. And a hammer blow on the mass will resist, so not transmitted to the hand. Well, that's a horrible sentence to say. But if you watch the video, it's really quite short, 30 seconds. But basically, what you have is a person getting a hammer and hitting an object that's over his hand, and it doesn't really hurt. And that's because all the force that travels from the hammer into the object will be dissipated throughout that object. But you couldn't really do that with any other object that's light, because if it's light, it doesn't have a lot of inertia, and it's not absorbing a lot of that force that's coming from the hammer blow. Okay, so the lighter an object is, the less inertia that there is, which means that the more force can be felt on the hand in this specific video. Okay, so have a look at the video and see what you think about it, and kind of imagine to yourself, what would it be if he used a piece of paper or a cardboard box, right? What if he used something else like a metal block, right? So just make sure that you are kind of looking at the right systems there, okay? If we're talking about Newton's third law, then we're looking at two objects, right, and one type of force. Okay, so hopefully at this point the foundation tier students are back and you are solving these exam style questions. Just remember that the very last question on this type of, in this problem, the last question there is a higher tier question, which it is labeled as such. So make sure that if you're foundation tier that you skip it. But if you're higher tier, make sure you try and answer the questions. This question is pretty straightforward. Multiple choice mixed in with a little bit of short answer questions. So make sure that you attempt every question, and let's see if we can get through it. So go ahead and pause the video and we'll solve this together. Alright, so hopefully you're able to see the screen. I know it's a little bit small, but if you have the PDF file next to you, you should be able to see the questions quite clearly. But I'll read it out for you if you can't see. So at the very top, When two objects interact, they exert forces on each other. So this is actually quite nice because they tell you Newton's third law right there. So for every action, there is a reaction. Which of the statements about the force is correct? The forces are equal in size and act in the same direction. The forces are unequal in size and act in the same direction. Forces are equal in size and act in opposite directions, or the forces are unequal and act in opposite directions. So, if anything, just try and memorize Newton's third law. For every action, there is an equal and opposite reaction. That's kind of the way that I've memorized it throughout my educational career. So, for this instance, the answer would be the third one. Forces are equal and they act in opposite directions. Okay, equal and opposite reaction. Okay, so here's the problem about the fisherman. So a fisherman pulls a boat towards the land, and the forces acting on the boat are shown in diagram 1. The fisherman exerts a force of 300 newtons on the boat, and the sea exerts a resistive force of 250 newtons on the boat. Describe the motion of the boat. So, first thing that you want to recognize is that you have opposite forces that are unequal, which means that you are going to get a resultant force, right? So the overall forces are unequal. There is a resultant force of 50 newtons towards the right, so the boat will accelerate towards the right. So for this one, you need to make sure that you specify that the boat will accelerate towards the right, right? Resultant force does not cause uniform motion. It causes acceleration. Okay, so that one should be pretty straightforward. Even if you put that the boat will move towards the right, you'll get a point there, but you need to be specific and specify that there is a resultant force towards the right of 50 newtons and that it will accelerate towards the right. Okay, this should be B, part 2. When the boat reaches land, the resistant force increases to 300 newtons, and the fisherman continues to exert a force of 300 newtons. So, describe the motion of the boat. Is it accelerating to the right? Is it constant velocity to the right? Or is it stationary? Now, for this one, you probably would have thought in two different ways. The first way, which is wrong, is you probably thought, okay, you have 300 newtons to the right, you have 300 newtons to the left, the resultant force is 0, that means it's at rest. And unfortunately, this is wrong because what you failed to do was take into account what was the motion of the boat before you took into the account of the forces. Okay, so was the boat already moving or was it already at rest? And in this case, in my personal opinion, it's kind of an awfully worded question because they should have specified that the boat was already moving, which you already should have solved in part 1, which is the reason why they asked a question like this. And so hopefully you understood that the boat was already accelerating towards the right from part 1. And so when the resistive forces increase to 300 newtons, you have a resultant force of 0. And if the resultant force is 0, you're either at rest or you're moving at a constant velocity. So this one, the correct answer is the second one. Okay. But luckily enough, in part 3, you are required to explain your answer. So on the next page, explain your answer to part B, part B, part 2. So in this case, the boat was accelerating when the forces were unequal, and when the boat reaches land, the forces are then equal, but was already in motion. So instead of being at rest, the boat is now traveling at a constant speed. All right, so hopefully that made sense. I know that it might be a trick question, but they got to make it a little bit challenging in one way or another. So there you go for the foundation tier students. And if you're higher tier, I'm going to answer the question on the next slide. If you're a foundation tier student, then what I want you to do is go ahead and solve the knowledge check questions at the end of the lesson here. Okay, so it should be 10 questions. You guys can go ahead and do that. Higher tier students. On the next slide, you have part 4. Now this one was really, really difficult because you probably thought to yourself, how am I going to get a number out of this? Because it actually asks you for a number. So there are, and I mean, even for me, I had to kind of look this up a little bit because I was a little bit stumped on how to find an answer to this that made mathematical sense. But upon reading the question closer, I found out there's a simpler way to do this. Okay, so another fisherman comes to help pull the boat, and each fisherman pulls with a force of 300 newtons, as shown in diagram 2. Diagram 2 is drawn to scale. add to diagram 2 to show the single force that has the same effect as the two 300 Newton forces. Determine the value of this resultant force. So the key word here is that diagram 2 is drawn to scale. So this is the part that I kind of read over and didn't think too much about it, but this is actually going to be really important, and I'll explain why in a second here. So remember when we were drawing different forces and drawing a diagonal resultant force, this is where that practice will come in. Okay, so you have your two forces, right? So each of those lines, the blue and the green, or sorry, the red and the green, represent 300 newtons, right? Same as the ones in diagram 2. And remember what we did when we kind of shifted each force across to make a parallelogram. And what I mean by that, so if I take the red line and I shift it downwards along the green line and made another line there, then what I would get is another red line at the bottom there. Okay? And if I did the same thing to the green line and shifted it towards the right so that it completes a four-sided shape, then what I get is this. Okay, and then what we did was we connected the corners, right, starting from the top left corner, and that would look something like that. Okay, and so that blue line represents what the resultant force of those two forces would be. Okay, so if I combined 300 newtons going to the right and then 300 newtons going diagonally towards the bottom right, and I put those two together, then the overall force is going to go in the direction of that blue arrow there. Now, you're probably thinking, how am I going to figure out how long or how big that blue line is? And this is where I was stumped as well. So if you got up to this point here, you actually earned yourself, I think, up to 2 marks. Okay, and this is where, where I said diagram 2 is drawn to scale comes into really important. What you're meant to do is you are meant to measure the 300 newtons. Because they are drawn to scale, they should both be the exact same length. And so whatever you measure out that 300 newtons to be, whether it's, I don't know, 1.5 centimeters or 1.8 centimeters, that becomes your new 300 newtons. Okay. After that, you are meant to measure out the blue line and see how big it is compared to your 300 newtons. Okay. So it's actually really important that this diagram was drawn to scale, because if it had not been drawn to scale, then you would have had to use a bit of maths to figure this out. But since it is drawn to scale, that means that your blue line should also be drawn to scale as well. Now, obviously, they don't expect everyone to be perfect, artists in this. And so they understand that if you drew it a little bit wrong and you measured it slightly off, then your numbers might be all over the place, which is why they gave you a range of anywhere between 545 newtons to 595 newtons. Okay? So I'm hoping that makes sense. I know it seems kind of silly to measure things out in physics and then to write down an answer for that, but that is the way that they want you to solve it. So I guess the lesson that you can take from this question is make sure you read everything, and if it says that it is drawn to scale, then they are technically allowed to not give you more numbers so that you figure it out using your ruler. And then we come to the knowledge check questions. So hopefully the foundation tier students, you're done with this. Just wait a little bit longer so the higher tier students can finish off this. But if you want to go ahead and pause the video and finish off this knowledge check here. All right, so here are your answers. And again, you're looking at Newton's laws as well as some other stuff that we may have learned in previous lessons. Okay, but that is the end of this lesson. Thank you so much for getting through this. I know it was quite difficult. If you have any questions about Newton's third law and specifically how it works, because I know it was quite difficult, make sure that you ask your teacher for some additional resources. There are some excellent things that you can find on BBC Bitesize or even on YouTube. If you go onto YouTube and type in Newton's third law, there are some really cool videos that you can watch, but also there are links in the booklet that you can use to go to certain YouTube channels that are really excellent at visualizing these laws. Okay, so thank you, and I'll see you in the next lesson.